Thank you for having me. Thank you for being here for my talk about databases unveiled. I'm glad I'm doing a talk about databases and not about dates, because apparently my PowerPoint presentation has the wrong date printed in. In this talk, a few movie references will come back, like this one from Raiders of the Lost Ark from Indiana Jones. Choose wisely. This is what the guy is saying to Indy when he needs to choose for the Grail, for the Holy Grail. In this talk, I will give a short introduction. I will take you through the different types of databases that I know of, and there are far more than that, and also their use cases and how you can implement them in your system. After that, I will show you some flexibility on how you can use these databases within your system and also be flexible enough that you can change these if you require different needs eventually. I will wrap that up and then come back with a short conclusion. This is about me. This is me with my daughter Milou of 3 years old. Previously I worked for Coolblue, where I worked on the search engine, where we moved the 300 shops that we had, like laptop shop, to the 2 shops they are having currently. And 5 years ago I moved to passenger information with NNS. 3 years ago I did a talk on the virtual JFOL about the passenger information system and how we migrated the 2 monoliths into the separate microsystems we have today. And still today we are building a lot of improvements on top of that, like the little animations of the trains going back and forth, and the letters that you can now see where you can take a seat for international trains, but also internal trains. 1 year ago I moved to the yard. Yards are within NS the locations where we do the cleaning, the maintenance of these trains after they run out of the passenger service. So after rush hour, we don't need them at that specific moment. We take them to a yard, we clean them, we maintenance them, we service them, and then they are going back into the system. And this is, like I said, 3-year-old Milou. Data is currently the most important part of the information systems within NS, and I think you all know that data is everywhere within those systems. So for example, the passenger information system, the screens you see at what time, what track trains are departing, but also like someone who's checking the weather on his or her destination. But also ProRail has a lot of information that they are gathering from their measurement systems on the tracks. We know about disruptions, like when signs and signalings and switches are broken. We will publish eventually a message like no trains between Amsterdam and Utrecht because of a disruption. Someone else is going to check his soccer results, and that's also data. It needs to be stored everywhere. And you can continue like, and for NS, for example, we also count the number of passengers, and all this information is stored in different ways within NS, and also processed in separate systems across our IT landscape. And one of the things that I want to point out is that data and our systems are very important to the service that we deliver to you as a customer. Last year, the 3rd of April, we had a big disruption within our system. The passenger system went down, the dispatching system went down, and that all because there was no active data coming from other systems into our systems. Eventually, we were restoring that information. We could do resyncs of most of the systems, so we were up to date again with the systems of ProRail, so we knew every train movement that was going to happen. But other systems, like our dispatching system, didn't know anything where our rolling stock was. And that eventually caused that we had to stop our passenger service that day. But it's not just us. For example, also other systems like this one is a news article from Toyota that states that their database scaling, their scale of the database, is actually one of the issues that they had to stop their plans. And what I have seen during my work at Coolblue and also at NS is that most developers using their database will fall into 7 fallacies that are stated by Loris Peter Deutsch, actually, the Sun Microsystem, from Sun Microsystems. And these are like that the network will always be reliable. You can send any query, it will always be delivered, and the data will always come back. There is zero latency. You will send that query, the data will be back immediately. There is no cost of the network, so to say. The bandwidth is infinite. So you could scale up your front-end facing system. You can send as many requests as you want, and all of them will be answered the same way over and over again. The network will be secure, so there is no one that will penetrate your network. There is no one that will change your data on the fly. The topology will never change, so it's steady. It will be reliable. You can predict. It is predictable in a way that you can use the system. And there is a single administrator. And this is really important, especially with NS. If you, for example, want to do a change in your data structure or in your access requirements, for example, you need especially more bandwidth, or you need a DNS lookup to ensure the resolvement of a DNS name. You have actually multiple points, multiple administrators you need to talk to and do a request. And one of the fallacies is actually that you expect there to be only one, and then you do the request, the change is being made, but the system will still fail because some other part of the system didn't see that request. And the network is homogeneous. That would like to say is that everything across that network will behave the same way. There is no part in that network that will change. But actually, if you start using databases, and especially when you start using cloud infrastructure or scalable infrastructure from a different service provider like Azure or AWS, you will actually see that these 7 points, and especially the topmost 3, are not that true. They will fail. The bandwidth is limited. There is latency. And how is your application going to react? And especially your database. Your database needs to be secure. You want to have the data reliable stored. How are you going to do that? Are you going to have multiple replicas, for example? Then this is especially true between the nodes within that database system. And one of the things that was discovered is the CAP theorem. I will touch upon this briefly. It was written up by Eric Brewer in 1998. Together with Douglas Twain. It states that there are 3 parts of a database system that you can optimize for. One is partition tolerance, and that states that there is a system that is able to operate even when the network fails. And like the 7 fallacies, if you really neglect them, you assume that there is always a network, but we now know that it will never be true, and there is always a failure in your network eventually. So all the systems need to be sure that they can behave with the partition failure. Consistency, that's then one of the 2 parts that you can optimize for. So we need the partition tolerance. All our database systems need to be aware that partition tolerance can happen. And then you can choose either consistency, which states that all the clients will see the same data all the time, or you can choose for the availability. And that will say that the clients are able to access and update the data rapidly, but whether the client connected to one data store and the other client connected to the other store are seeing the same data, that's not always the case. Actually, during the upcome of our database systems in the cloud, especially the AWS and Azure, we came to the conclusion that this system is a bit too narrow. There are actually more options that you can choose of, and that's the thing that Daniel wrote up in 2010. That if there is a partition within your network, so you have multiple nodes for availability reasons, and these partitions, these nodes, are not able to connect to each other, is there a way that you can optimize? So if no, then you can choose between 2 things, where the PAC theorem will only say that you can choose for consistency, where you can only choose for consistency, This one actually says you can also choose for latency. So you can say, I want utmost consistency, then that would say that you do consistent writes across all of your nodes synchronously, so the data is everywhere stored, everywhere all the time, or you do the latency. So if you have no partition, you still write to one part of your system, and the latency is up to you. How long would it take for the data to replicate, and is that still valid? And if there is a partition, you can actually choose, do you want the availability, so that data can always flow through the system. For example, you can still read all the information from your different data nodes while the network is split in two, or you choose for the consistency, and this would eventually mean that your system is going down, or for example, for writes. So then you can still read, but since you choose for the consistency, there is no way to update the data anymore, because you still need the decorum, or you need at least the network to operate well. And from that, there are two paradigms that most of you will know. You have the acid paradigm that says that every change you do is atomically consistent in isolation, so no other clients will see it during that change, and durable. And on the other hand, and that's especially true for NoSQL databases, you have the base paradigm, which states that it's basically available all the time. The soft state, so you have no way of knowing whether your state that you receive from the database is the actual latest state there is. And that flows through into eventual consistency. Eventual consistency is basically that as long as at a certain moment you stop making changes to the system, that eventually, over time, all your clients will see the same data because it will be replicated through the system. And these two are really powerful, and you can really choose whether you want one system or the other system for your data storage. Next, I want to take you through a few use cases that we see with NS. And I want to start with a simple database for our front-facing customers shop, where you can buy tickets for a day out, for an activity. In this case, the Light Festival in Amsterdam, where you can buy a ticket. This data is typically short-lived. You want it to be there. You want it to be able to be persistent over the course of maybe a few hours, but it's not like it's your most valuable data there is at this certain moment. This shopping basket, you can lose it if you want, especially with the Spoordeelwinkel. Mostly people will only buy a few tickets. If that session would fail, you could say, okay, we have one failing customer, one unhappy customer, please check out again and create the order again. So for this use case, we use a key value store, which are mostly in memory. So they are really fast. We can update them really fast, really quick, read from them really fast. The key is mostly the reference, in this case probably the session token, and the value is the basket of the client. They are really fast, but they are not durable. And I know that's not the case, because for example Reddit you can make durable. But in most cases, it's not durable and it only lives in memory, either in a cluster or only a single data store at the machine itself. And so while it fails, you need to have one way and another to retrieve that data again. And for the shopping basket, it's basically the user doing the order again. But in other cases, it could be that you do a resync or retrieve it from a more durable data store. Two examples of this is, like I said, Redis, but also one other important thing, one important key value store that we are using within NS is etcd, which is actually the data key value store within Kubernetes underneath to do lookups for discovery and service discovery. Another use case, and probably most 60% of all the applications within NS and also worldwide, based on a study, are actually using this, is the relational model. So you have a table or you have one piece of data and you have related data based on that. For example, we have a station. On these stations we have tracks. On these tracks we have facilities like a kiosk shop where you can buy sandwiches, those kind of things. All that information for us is stored in a system that we call TOPS, and it's basically the master data store for us. So this contains all the information about what train series we are using, what the names of the operators are that we know, what locations we have to do maintenance, and what locations we have for our crew to drink coffee. That's all stored in these databases. It is really powerful to do separate queries based on the needs for that specific application or that specific view. And they are really strong on consistency, relational database, so to speak. You can store, and it will be asset compliant. The transaction level, make sure that it's isolated for that specific use case. And since it's strong on consistency, it might introduce some latency. And for this master data, that's not that important. It is important that during the writes, the data is consistent. That's what we most value. But after that, when we are reading it, that latency is neglectable because we are using it in different systems. For example, in combination with a key value store, where you can read it back from quickly instead of doing the queries all over the time. But one thing we found out within NS, and I think that's true for most of the part, for most companies, is that these databases are quite hard to scale. Most of the time you need to scale them vertically first. You could add read replicas, but that will interfere with maybe your latency or your consistency level. So, and one downside of it is that when you want to do this properly and want to have a proper performing database, you might need to do a big design up front, including indices, including what size of data, how many fields, how big does the cluster needs to be to support your requests. The parts that we are using is mostly Postgres for the main applications. We have some legacy applications that are really strong, dependent on Oracle. And MySQL is also one example. And then I don't think, I mentioned it here, but I don't think we are using it that much within NS. When you are really sure what the key of your object is, but the data related to that is too big to put in a key value store and you want to be more flexible and more durable, then the next database is probably for you. This screen shows you a train, in this case a non-passenger train from Zwolle to Hon. I don't know especially, sorry. And you will know for this train the date and its train number. And based on discussions with all the European operators within Europe, we say that the train number needs to be unique for that specific day. So this is a really strong key. If you know these two fields, you can look up any train information. So for us, within NS, we use a document store based on that key to store all the information about the train. What is the operator? What stations is he going to stop on? For how long? And even what track? And the delays, the time, the speed of that train. So this is really strong if you know the key of that data source. One downside of using a document store for this is there is no easy way, most of the time, to say, I want to know all the trains that are stopping on Deventer, DV, in a specific time frame. Most document stores are really strong in availability. Since the data is being replicated, the master and the primary are being shared across the cluster, sometimes based on a hash key. You can actually mostly write still consistent to a store, and also read will be kind of almost available. They are great to scale, especially with reads. Like the embedded structure, so if you have like the relations of the stations and you want to reference them, you either need to include them, so you need to include all the station information in this document all over the time, but that will introduce issues when you want to, for example, say, I want to change this station name. You need to do all the documents that embed that document to be updated. And I think Mongo made big steps to have actually referenceable subdocuments. A really powerful example of document storage is that they are easier to change with their data. You could easily add more fields, for example, for data migration. If you have like a different structure than you want to use for a different system, you can actually extend and then later remove the fields that you use during the migration. And some great examples are Mongo, a really powerful search engine, which is underneath actually a document store using indexes. So Elasticsearch would even be able to say you created one document for that specific train number, and you could do queries on these indexes that it creates for example, Deventer. And also Azure within NS is also a document store. And if you are more AWS-minded, DynamoDB is the one. One other type of database, of data store that we are using with NS is for our travel planner. So we have all these train information train information fields, documents, but these are really hard to say, for example, I want to go from Utrecht to Edes, Wageningen. For that, you actually want to use a graph search. Graph searches are really powerful for route planning, like here. They are strong in relations. Also, for example, Facebook is a great example of that, where they can actually answer the question if you are friends with friends and how many steps and how many relations are in between, and if this might be a friend of yours, and if you are interested in this guy or this person to connect with. They mostly include pathfinding algorithms like shortest path, A*, to find paths between two nodes. And two powerful examples that I've seen within NS are Neo4j, and also Cosmos actually has a graph database wrapper, Gremlin, I think, on top of that. Another specific use case that if we that is really hard to scale and really hard to do currently with just a regular relational database. If we have our train units that run across the country, and most of these trains have like 9,000 data points that range from external temperature sensors to specific sensors on each wheel, what the temperature is, how many movements, how many rotations each wheel is making, internal temperature, water level, air pressure, whether doors are open or closed, pressure sensors, well, almost everywhere, like 9,000 data points. And we want to use these data points for analysis. Predictions. Is a wheel going to wear out eventually? During our autumn season, the leaves on the track will actually wear down wheels separately. If there are more leaves on one track to the other track, there could be a difference between the wear and tear on different wheels. And that's something we want to measure and also predict, so that on our yard we can actually focus on the trains that have the most wear and tear, so that these can be back in rotation, back in the passenger service more quickly, and even before they actually fail and have to be taken out of service. Because of these 9,000 measure points that notify us probably each second or maybe once a minute, a regular database won't help. Another great use case is probably your own system monitoring. What are request times? How many messages are you sending out through your system? So that's actually a great use of a time series database. They are strong for metrics and real-time analysis, and you will just extend and append one log at a time. With each measurement, you will just extend and extend and extend. And a separate process will eventually roll over and do your analysis. They are great for huge data ingress. So if you have a lot of data that is coming in and flowing into your systems, and you could do even eventually predictions with them. Great example is Cassandra, but also like I showed you the dashboard for our passenger information system that actually uses Prometheus, which is also kind of a data store for time series. And what I want to focus on is that you need to choose wisely. For whether you want one database or the other database, you want to first check your consistency requirements. Do you always need the highest consistency? Especially with NS, always the discussion we have with the business, the consistency of the data is the most important. I want to show you an example why that not be the case necessarily. One other thing you need to look at for your database option is the availability requirement, but also like how is it to recover. So for example, if you have a Postgres database with a standby failover, that's fine, that's nice. You could fail over to the other data set, but how are you going to go back? Is there a way to recover from that? Would you just go back eventually, or would you stay in that state forever? And then the latency requirements. The latency in the consistency, if you don't need the consistency on that level, how long is it acceptable for data to be replicated? And I think one of the great solutions to actually use databases and also be flexible in the implementation and also in the ability to change them eventually is CQRS, the command query responsibility segregation. This could actually help also in the different requirements you have. For example, like I showed you with our TOPS, our master data records, the right side is really important. It needs to be consistent. And probably most dispatching systems are really consistent on the right side. But it is fine that the data is eventually out there. So maybe the storage, more customer-facing or more consumer-facing, could be less consistent or more available and less consistent. So in this case, with CQRS, you could actually split your model and you split your data source for the write and the read side. And you could actually both optimize them for the access patterns that you have. Is it, for example, really read-heavy? You use Cassandra on one side. And is it write-heavy? You could use Cassandra on one side and just do the predictions on the other side and store them in, for example, the Postgres database or a document store where you can really quickly access the results of predictions, for example. So to make it more visual, if you have one consumer or one application that does the writes in one side, and then you need a way to replicate the data from one side to the other, and you could store them for the read side so that you have optimized access patterns, optimized storage for these queries. And like I said, when I have a discussion with my business, most of the time they will say that consistency is the most important between ProRail and NS, or even within the system that we have. But in this case, I want to actually show you that it's even our actual world outside is eventually consistent. So let's say in this case, NS sees that on the platform in Rotterdam, there are a lot of Feyenoord supporters that want to go to the stadium. Currently, they will actually do a call. Can I operate an extra train from Rotterdam Central Station to Rotterdam Centraal? This is still either a call or it could be an automated process, but there will always be some delay in actually filling this request, noticing that there are people that want the actual, that there is actual demand for this train, and doing the call. We need to arrange crew, we need to arrange rolling stock to actually operate this train. We need to have this rolling stock on the platform, which is something that the yard does. And ProRail in this case would say, sure, we will say thanks. And then at that specific moment, it will be filled into the systems. It will flow through the systems and eventually be everywhere. For example, actually on the station, on the sign on the station. But the app could be like a few seconds later. The other operators, like 9292, other apps could be 1 second faster. So our real-world example is already eventually consistent. So in that case, we could have opted for a less consistent database with less latency or more latency to actually introduce the access pattern that we want so that we can access it quickly, on a train number, for example. So back to this picture, there is one other pattern that extends on this. I want to go over it briefly, and that's actually using event sourcing for the replication. In that case, you will actually store events, so not like a piece of state, but you will actually store the changes. For example, I want to schedule a train, and then I scheduled that train, or I made that request for a train. And these events you can probably store best in an event store, but also other data stores are able to be used as an event store. And then you only have like different stores for your projections. And that's basically the access pattern where the end user is focusing on. So that could be a view for our dispatcher, that could be a view for the station sign, that could be a view for our scheduling software. And that will eventually be like a diary. These event streams you can roll back, you could replay, you don't want to change them, but it will help you in debugging or changing stuff or replaying stuff in a different way. And you could actually simulate real-world scenarios and see what happens in other systems. And these events can also be shared through the domain with other applications so that they can all build their own need and their own projection of the real-world example. During my career at NS, I found a few situations where we actually built our software around the database model. And that's, I think, a shame, because it will actually fix you in that position and make it hard to change your data store eventually. So I know for sure there is on the current moment in time also a talk about the Hibernate implementation, whether you need it. This is one of the examples where you actually see like the API and Hibernate examples within the domain model. And I think that will limit you in the flexibility and also in the options that you have later on. So if you want to look at, for example, clean architecture, you actually say that the domain model is your most important layer within your application, and it should be completely free of any infrastructure-related code. So on the blue circles, you will actually see the DB, the UI, and also like the web-related controllers like RESTful APIs or event hubs, for example. And that's, so in this layered architecture, you will actually focus on the domain layer itself, where the domain logic will live, and there is a separate layer that will actually operate on the storage mechanism. And this layer architecture will eventually help you in switching for the storage layer underneath during this inversion of control. So one great example, or one example of what we just did, we have just a domain class with a few primitive values for our train. This could even have some validation, for example. And then there is a infrastructure package where you do the actual implementation of how to store this, in this case, for a relational model. And it makes it really easy for you to create a different implementation of your interface and store it, for example, in a document store. To come around a bit, I want to plot my experiences of databases on this graph, focused on strong and eventual consistency and the small or large data store data requirements. So on the left, you have a small data set, for example, key values, that could be strong consistent and is really helpful for fast access and something that you can replay or can reload from a different data store if you want to need it, or for example in cases like login, that if it fails, that the user can just re-log in again once again. On the other side, graph databases are able to use big sets of data, but most of the time they will be eventual consistent. A document store, and I know for sure that MongoDB is focusing on making it more consistent every time. And also DynamoDB can currently have a transaction of spanning 10 documents. But I still consider them less consistent than other data stores. But they are really good in big data, and especially when you have the right key to pinpoint your document on. Time series are used for really huge ingress of data, but they will be eventual consistent, and especially when you want to do predictions, that will always take time to do these predictions, and that's something you need to take into account when you are using such a database. And on this one, I think relational databases are the best thing you can have for a startup project that needs real strong consistency, and you have a limited size data that you are spanning. So my conclusion, choose wisely, but what I want to give to you is that you need to be sure that you can adopt. So starting with, for example, a Postgres database, because it's easy to use locally, because it's easy to write separate queries for these separate views and separate business cases that you have, could help you in really speeding up your development process and having a quick head start. But then eventually your project will grow. You are doing more trains a day, you are processing more time series a day, and in that case you might want to adopt. So if you have your layered architecture, that makes it easier to change your implementation later on. I want to give to you like plan ahead, but also not too far ahead. I think one of the worst things is that we can do is that we think we can plan like 5 years ahead. I would rather focus on a few months, maybe a year upfront, and then see how your system is progressing, how the data is progressing, and change your implementation based on that. During the research, during my development career, I also want to be sure to give this to you. Don't trust the vendors. For example, Mongo, but also Postgres. Postgres is stating that they can be used as a document store, that they can be used as a graph store. Cosmos is saying that they can be everything, and Mongo is also trying to be more consistent over time. I think you definitely need to read their documentation. Be sure to test their implementation. Try to fail. Try to break their system. Try to do a recovery, and maybe not on production, but maybe on a staging environment with more like production lake data. Try to see how the system is behaving. Don't trust their publications on their word. Don't trust that they are saying that they are tolerant for a failover, but test it yourself. And before opening the candy store of all these different databases, make sure there is knowledge in your team to support this database. From a recovery perspective, from a business continuation perspective, but also from a development perspective. If you want to implement new features, new functionalities, be sure you are comfortable with using that data store that you have chosen. And like I said, always experiment and learn. Try to use new products and see what they can bring you. For example, within the data stores of NS, we have really powerful functionalities, for example, with the graph storage, where we can see relations between trains pretty quickly now. That's something that we learned during an experiment and not something that we planned for. So once again, choose wisely. And if there are any questions, please ask. Yes?
The part about the vendors' promising things,
Yeah.
sounds interesting to me. Can you explain a little bit, give some examples, for example, in Postgres?
Yeah.
They promised and you found out this is not totally true.
Yeah. From my experience during the passenger information system that we rebuilt from the two monoliths that we had based on an Oracle cluster, we moved to a Mongo database at first, or a Postgres, or a document data store at first. What was really important to us is that we could pinpoint every train based on their date and train number, like the example that I gave, but also that we could look up based over time. So if we want to see all the trains that are departing within 90 minutes. We found out that, for example, Mongo was really quick in that and doing those kind of query. On the other hand, Postgres was promising like we could be your JSON document store like that, but doing these JSON queries on that time field embedded deeper in the document was one kind of thing that just didn't perform at all when the data size grew. So that's one example. And I'm pretty sure actually that during the later versions of Postgres that has been improved, but in the way NS is working, we are also reliant on vendors that needs to install these databases, and we were at that moment based on an older version.
Any experience with event stores at NS?
Not in NS, unfortunately, not for me. I'm not sure whether other team members are actually using event stores, but within Kublu we had event stores, and we were actually fond of our Postgres implementation. We used one single table. We had a high consistency on that event store table with the isolation level correctly set so that no other transactions would interfere with that specific aggregate. We were looking into other options, but like I said, I moved away from Guru like 5 years ago, so I'm not sure how that progress went. Then thank you.